Hey people, let's start learning for earning.
Welcome back to The Explainer. You know, Henry Ford completely revolutionized the world with the assembly line, but honestly, if he stepped into a modern factory today, he wouldn't even recognize it. Today's mega factories aren't just a bunch of steel and sparks anymore, they are massive, breathing organisms, and they're powered by a hidden, incredibly high-speed nervous system.
Okay, let's dive right into this. I want you to just pause and imagine the sheer complexity of industrial automation for a second. You've got thousands of sensors, motors, valves, and robotic joints, and every single one of them needs to act with split-second timing. If just one valve opens a fraction of a second too late, an entire production line could halt, or worse, completely fail. So how on earth does a sprawling facility choreograph all these moving parts so flawlessly?
To really grasp this, we've got to look past the steel. We have to think of the modern factory as a biological organism. Seriously, it has a brain that makes decisions, muscles that do the actual heavy lifting, and absolutely crucially, a hidden nervous system that lets that brain communicate with those muscles in real time. Today, we're going to trace the evolution of this industrial nervous system.
Section 1. Brains, nerves, and muscles. It's actually wild how neatly these industrial components map to biological functions. The brain is the Programmable Logic Controller, or PLC. This is the central computing nexus where the automation program is actually running. The nerves are the physical networks, the copper wiring, the Ethernet, and the fiber optic cables carrying all those signals. And the muscles? Well, those are the industrial drives and remote input/output, or I/O blocks, located way out on the factory floor, physically executing the commands.
Take a look at these Siemens Master drives right here. These are serious heavy-duty motor controllers used for optimal motor operation. Basically, they act as the passive executioners in our network. The central brain sends a request message with output data down the network. Let's say a specific set point speed. And these drives receive that command and physically spin the motors to match it. They are literally the brute force of the entire operation.
And here we're looking at the distributed nerve endings. These are Beckhoff I/O modules. These modular devices sit right down at the field level. They take in physical signals from the real world, things like temperature, pressure, or position detection from sensors, and they convert them into digital data. They're out there gathering input data from the environment and formatting it so the factory's brain knows exactly what is happening at the very edges of the plant.
Section 2. Profibus, master-slave polling.
So, what language are these components actually speaking? Well, historically, it started with Profibus, which relies on a master-slave polling method. Think of the master, which is usually our PLC brain, as this incredibly strict, highly organized boss. It literally points at each passive slave device on the factory floor, one by one, in a continuous cycle, asking, "Do you have data?" A slave device, like an I/O transducer or a network drive, can only respond to the prompting master by sending a response message. The cycle only wraps up once all the connected slaves have been polled in order, and then, boom, it starts all over again.
And this brilliantly illustrates that dynamic. Notice how the master sits right at the top, initiating that downward request arrow. It's super important to note here that all Profibus slaves have the exact same priority. They are totally passive. Even if a valve has a critical pressure warning, it has to wait politely for the master to ask for its data during the regular polling cycle. Every single piece of communication originates from the master.
Section 3. Profinet, the Ethernet upgrade.
Now, as these factories grew larger and the processes got vastly more complex, waiting in line for a strict boss to ask for data just became a huge bottleneck. The whole system needed a massive upgrade in speed and bandwidth. The crucial point here is the shift in the physical cables and speed. Profibus was largely built on older RS-485 serial cables, but Profinet, it brought the factory floor into the modern IT age by utilizing switched Ethernet with a bandwidth of 100 megabits per second. And honestly, even more importantly, Profinet introduced full duplex operation. That meant simultaneous sending and receiving became possible. Devices no longer had to wait for a single one-way street to clear up before they could start talking.
Looking at this Profinet I/O architecture, you can see exactly how that relationship's changed. Instead of that strict master-slave polling we just talked about, it shifts to a provider-consumer model. From a communication standpoint, devices on the Ethernet are treated much more democratically. The I/O controller and the I/O device establish these really clear communication channels. There's a dedicated real-time channel for I/O data, and critically, a real-time channel specifically for alarms. This lets the network be used so much more efficiently.
Section 4. EtherCAT, processing on the fly.
But, you know, engineering never really stops pushing the envelope, does it? Let's move to the next evolution and see how this builds, because even standard Ethernet had limitations. Standard Ethernet requires packets of data to be received, interpreted, and copied at every single connection point before moving on. In a factory with thousands of sensors, those tiny little delays really add up. EtherCAT fundamentally changes how Ethernet packets are handled to achieve blistering, almost unbelievable speeds. When a standard Ethernet frame enters an EtherCAT node, it doesn't stop to be unpacked by bulky software protocols. Instead, a specialized hardware chip reads the data addressed to it and simultaneously inserts its own new input data right into the frame, all while the frame is actively moving downstream. It literally processes the data on the fly.
To pull off this kind of dynamic processing, every single EtherCAT slave device uses an EtherCAT slave controller which operates entirely in hardware.
Because it completely bypasses the software protocol stacks and CPU runtimes of the slave device, the telegram is only delayed by hardware propagation times. Guys, we are talking about delays measured in just a few nanoseconds per device. The frame just blows right through the nodes at full speed, picking up and dropping off data like a high-speed bullet train that never even stops at the station.
Because of this hardware-based, on-the-fly processing, the performance numbers for EtherCAT are, well, they're simply staggering. 30 microseconds. That is how long it takes for an EtherCAT network to update 1,000 IOs. Just to put that into perspective, 30 microseconds is vastly faster than a human blink. In a single Ethernet frame, EtherCAT can exchange up to 1,486 bytes of processed data. That equates to managing almost 12,000 digital inputs and outputs, all in a fraction of a millisecond. It's wild.
Section 5. Why this speed matters. So we've thrown around some incredibly technical terms and mind-blowing speeds here, but why does a factory actually need this level of performance from its nervous system? Well, this blazing speed and massive data capacity allow for modern automated processes that were literally impossible before. Because the network updates so incredibly fast, it ensures flawless mechanical synchronization across hundreds of robotic arms and drive shafts. Plus, this speed allows for highly available redundant systems. In EtherCAT, for instance, you can actually run a cable from the last node all the way back to the master, creating a ring topology. If a cable snaps on the factory floor, the system detects it and routes the data the other way so fast that the machines don't even know there was a physical failure. It absolutely protects the plan from catastrophic downtimes. So we've journeyed from the strict, cyclical polling of Profibus, through the democratic Ethernet of Profinet, all the way to the nanosecond, on-the-fly hardware processing of EtherCAT. We've seen the brains, the fiber optic nerves, and the heavy-duty muscles that make it all happen. But it leaves us with an incredible thought to ponder. As our factories reach these near-instantaneous reaction times, effectively removing the physical limits of communication, what will the automation of tomorrow be capable of building? I really hope this explainer has sparked your curiosity about the hidden networks operating all around us.
Thanks for watching, and please like, share, and subscribe for such more content and appreciation. Make sure to comment your questions and